Okay, now I'm going to do the third part of the Gull's part. It will not be quite a proof because there are some jumps which are made which either require assumptions or regularity conditions or certainly discussion. But anyway, let's look at the idea and show that there really is a theorem here, though what exactly the assumptions should be is still to be discussed. Okay, so let's suppose that there's given mathematically a probability space, and on it are defined random variables a theta and b phi, taking values in plus or minus 1. Theta and phi are angles between 0 and 2 pi. And of course, in a little while, we'll suppose that that probability space and those random variables reproduce the singlet correlations. In other words, the joint distribution of a theta and b phi for any particular theta and phi is the one which comes out of the quantum mechanical calculations, which we call the singlet correlations. Now, suppose not only do such objects exist mathematically, but they are also constructible in the sense that one can actually write a computer program which can simulate an infinite sequence or a very long sequence, omega 1, omega 2, etc., independent and identically distributed drawings from omega under the probability distribution, probability measure P. And similarly, suppose also those functions a theta and b phi, those random variables actually, so of course they correspond to functions a of theta and omega and b of phi and omega, and suppose they are so constructible that we can actually program them. So we can simulate the joint distribution of a theta and b phi for any theta phi, and in fact for many thetas and many phis at the same time. Then I'm going to suppose that that simulation is also reproducible in the sense that in the following sense, suppose it is actually not random at all, but it's performed by a pseudo-random generator, and so it's just a deterministic sequence which depends on a seed and an algorithm in which there may be some parameters. So it's actually a deterministic sequence, but that means if we put the same seed and the same parameters on different copies of that computer program, we will actually reproduce the same sequence omega 1, omega 2, ... of drawings from omega p. But still, I'm going to think about that sequence in two ways. One as something deterministic and computed on a classical computer or saved on the hard disk of a computer. So it's clonable. One can make it many times on different computers and it'll be just the same. But at the same time, I'm actually going to do some probability theory in which I will assume that omega 1, omega 2 are IID drawings from omega with probability measure P. And I don't think that's a contradiction, but one needs to think about it. Okay, so this all means I can set up two separated computers which can both realize the same sequence, omega 1, omega 2, ... And then for any input sequence, theta 1, theta 2, ... and phi 1, phi 2, ... I will be able to produce output sequences xi equal to a of theta I omega I and yi equals b of phi I and omega I. So the outcome xi depends on the ith angle theta I, but it doesn't depend on any of the other angles. And similarly yi. Now, so suppose Bell's theorem is not true, and that indeed we can simulate omega p, a and b to recreate the singlet correlations. Then we can do a number of different experiments, every time starting with the computers in the same state and generating the same infinite sequence omega 1, omega 2, etc. But feeding the two computers different. So one computer has evaluates A, and the other computer evaluates B, and we can give both of those computers arbitrary sequences of angles, and we can repeat this as many times as we like. So one thing we would find if we do a number of those experiments is that if theta I equals phi I for all I, then the outcomes should be equal and opposite. Of course, the singlet correlations say that the probability is 1 that they will be infinite, that they will be equal and opposite. And so I guess this means that when the sequence goes to infinity, it won't happen very many times that theta I is phi I. But I'm going to make a stronger, not so much deduction as an assumption. I'm going to turn this into the assumption that the computer program B is actually the computer program for A, but with a minus sign added. So that given the same angles, the second computer does produce the negative of the outcomes produced by the first computer. And secondly, I'm going to suppose that with some infinite sequence, with these infinite sequences, one reproduces the singlet correlations. So in particular, this implies the following. Suppose I give one computer A, an IID sequence of angles, settings, theta 1, theta 2, etc. And then I take that same sequence and I shift it through delta, mod 2 pi. And I give the second computer the angles theta I plus delta. Then if our simulation is good, the observed correlation, and I mean here the physicist correlation, the product moment, the observed correlation between the two sequences of outcomes should also be the singlet correlation minus cosine of delta. So putting the first assumption or step together with the second assumption or step, I'm going to assume from now on that the sample correlation based on a sequence of size n performed in this way corresponds to the negative cosine minus cosine delta. But we also know what it must do from the point of view of treating those angles, settings, theta I as IID samples from the uniform distribution on the circle, and taking those omega i's to be IID samples from capital omega under distribution P. By the law of large numbers, that same observed correlation will converge to a double integral of A theta omega, A theta plus delta omega, or a double expectation you could say, where theta is distributed uniformly on 0, 2 pi, and omega is drawn with probability measure P from capital omega. Now, the interesting thing starts, and I'm going to suppose that my function capital A for each little omega has a Fourier series. And of course, so this is assuming some measurability, of course, because I now want to integrate the product of the function A as function of theta for given omega, its product with e to the minus in theta, and for any n in z, for any integer, positive or negative. This generates a sequence, Cn, a random sequence. It depends on little omega because the function A depends on little omega as well as theta. But the random function or random stochastic process A with time index points on the circle is converted into an infinite sequence of complex numbers, random complex numbers, Cn of omega. Now, the exponential functions e to the in theta, when we run through all of n in the integers z, are an orthonormal basis of the L2 space of complex valued functions on the unit circle with probability measure on the unit circle equal to Lebesgue measure divided by 2 pi. In other words, the uniform probability distribution. And that means that we can write, at least in L2 sense, that A of theta is sum over n in z Cn e to the in theta. And this is an equality in L2 sense, but it's also an equality between a random function on the left, well, between two random functions, two random elements of L2, because they both the Cn's and A also depend on little omega, and little omega comes from distribution P. Okay, now we can very rapidly get to some nice conclusions from here. And the first thing is we're going to make the observation that the function A is actually a real function. So it was a bit funny looking at its complex Fourier series or Fourier expansion, but okay, one can do that. But because A is real, its Fourier series is equal to the complex conjugate of its Fourier series, and that's written down there. Sum n Cn e to the in theta is sum n Cn bar, complex conjugate of Cn e to the minus in theta. And so by the uniqueness of that expansion, the coefficients Cn are related by Cn is the complex conjugate of C minus n for all n. Okay, so that's an important little fact to remember. But let's continue. So the empirical correlation, when we're giving our two computers random angles uniformly distributed around the circle, but Bob's angles are always shifted delta with respect to Alice's angles, the empirical correlation converges by the law of large numbers, and we have to discuss if this happens uniformly in delta and things like that, but I'm not going to go into these niceties. It seems reasonable to expect that rho n hat of delta, which is also a function of little omega, converges to the double integral of a times a shifted by delta, and we're integrating with respect to theta around the circle, uniform distribution, and omega from the probability distribution P on omega. So let's substitute now the Fourier series for A, and it's an infinite summation. So this limit of the empirical correlation, which we observe, can observe for each delta, is rho. I'm going to call it rho of delta, and we can compute it by substituting the Fourier series in two places, and we get a double integral and a double summation. Summation over n and a summation over n prime, e to the in theta, e to the in prime, theta plus delta. We integrate over theta from 0 to 2 pi, and we take the average over little omega, which enters into the Fourier coefficients Cn prime. Now, when we collect just the part of that whole business which depends on theta, we pick up two exponentials which we combine and an integral. And we pick up the integral over the circle, e to the I, n plus n prime times theta, d theta over 2 pi. And that equals 1 if n prime is minus n, when the exponential function becomes the constant 1. We integrate the probability measure over the space 0, 2 pi and get 1. And otherwise, because these functions are an orthonormal basis, and this is just the inner product between e to the in theta and e to the in prime theta, we get 0. Otherwise we get 0. So our double summation becomes a single summation. The integral has been performed, been evaluated, so we get a Cn times a C of minus n, sorry, a C bar of minus n, because n prime is minus n, and so the Cn times Cn prime reduces to the absolute value of Cn squared. So we end up with the integral minus the integral over omega, summation over the integers, positive and negative, absolute value of Cn squared, e to the n delta. So I have to put back an n then, I to the n delta dp is the integration over little omega is an expectation value, so we end up with minus the summation over the integers, expected value of the absolute value of Cn squared. That's the same for negative and positive n, and it's a positive real number, e to the in delta. But what was rho of delta? Rho of delta is minus the cosine of theta, and it has a rather simple Fourier series. Its Fourier series is minus a half e to the I delta plus e to the minus I delta. So what does this tell us? This tells us that all the Cn's are almost surely, in other words, probability 1, 0, except when n is plus or minus 1, when the expectation of the absolute value of their square is a half. So a of theta is C1 e to the plus I theta plus 1 I theta plus C minus 1 e to the minus 1 I theta. But this cannot be, because a is a function which only takes the values 0 and 1. Okay, it's a random function. C1 and C minus 1 are random variables, but there's no way that realizations of a can be almost surely equal to or look anything like a cosine, a linear combination of some cosines. So that's the proof. Impossible.